All right, this is page 209 of the notes. And this is a hypothesis test for the slope of the regression line. Now, most of the time, this information is going to be provided for you in a computer printout. We're going to go through it or what we expect you to have to know. So this is going to go fairly rapidly through this, and we're going to present it in a way we expect you're going to have to answer it on the AP exam. So using the data from the airfare and distance scenario, perform a hypothesis test with an alpha level of 0.05 to determine whether or not the slope is significant. Very first thing you need to do is define your variables. Well, we're going to say X is the distance traveled in miles, and Y is the airfare charged in dollars. So we need to start off by defining our variables. Then we need to write our null alternative hypothesis. So beta 1 equals 0. Beta 1 does not equal 0. And it's almost always going to be a not equal here. So don't worry about whether it's a greater than or less than. I think it's only occurred one time that it wasn't, that they used a less than. And when they did that, used a greater than symbol. And when they did that, they actually gave it to you. I don't think that's not likely. So we can plan on it being a not equal 0. Because if the slope is not equal to, basically you're testing, is the slope something other than 0? Is there a linear relationship? Then we need to write out what it is that means. HO, there is no linear relationship. HA, there is a linear relationship. Please make sure is a linear relationship between our variables X and Y. And then you need to explain what beta 1 is. So beta 1 is the expected increase in airfare for every 1 mile increase in distance traveled. Notice we didn't put the slope value in there because we don't know what it is yet. But it's basically, hey, what is our slope? How much is it changing? So our conditions. In this particular case, they didn't tell us it was a random sample. So we're going to have to assume that the flights information is representative of those domestic commercial flights, specifically from Atlanta. But we're going to have to make that assumption. Normally, they're going to tell you, hey, a random sample, and you'll just state random sample. So that doesn't change. But here's where things get a little different. First off, we need to reference our scatter plot. Now, and say that it appears to be linear. I've never seen them have on a test actually have you draw it, but we did. We put our data in the stat edit, we drew it. You don't even have to include the line, but basically, do you see that there's some sort of direction? If you can't tell a direction, then probably isn't linear. If you can see a definite pattern to it, not linear. Here, I don't see a pattern other than the fact that drawing a linear line would probably be my best guess. And that is for the scatter plot, not just the residual. And it says see page 202 and 203, because we actually have those drawn into the notes on page 202 and 203 if you wanted to see them. But we already entered the data into the calculator. And if they wanted you to check it, I'm pretty sure they would have given you the graph and say, hey, does this meet yes or no? The next thing, the residual plot. So I'm going to go ahead and change my calculator real quickly. And we actually drew that as well. And it's also on page 204 of the notes at the bottom. And if I go zoom 9, I end up getting a scatter plot. I notice there's no pattern, no apparent pattern. Yes, it's more dense over here because I have more data points, but there's no pattern. So the residual plot is random. And you might even want to say the residual plot and exhibits no pattern. All right. Then, of course, we get to do our favorite graph of all times, the box plot. So we need to check to see whether or not the residuals are reasonably symmetric and with no outliers. And so we've already gone and we had stat edit. We calculated our residuals. We placed them in L3. And just as a reminder on how to do that, you go to the top of L3 and you're going to go second list, scroll down on your calculator, and it's going to be in different spots, and you're going to find resid and press enter. There it is. So I have my residuals. Now you're going to go to second stat plot, enter, make sure that's turned on. You still want the first graph, but I'm going to make sure my we no longer want that graph. We want the box plot graph. And our list of interest is our residuals themselves, which are in 3. So second 3, zoom 9. There it is. Obviously, in this case, well, we can use the trace function as a reminder to get the important values. When I look at those important values here, it'd be very, very difficult to draw a scale. So I'm just labeling the important values. That's all I'm going to do with that. And when I look at that, it's like, you know what? I don't see any outliers. This appears to be reasonably symmetric. It's okay to assume that the residuals are approximately normally distributed. All right. If you had more than 30 values, then you'd be good to go. But here we didn't. Here we only had 18. Okay, SB, standard error of the slope. They're not going to ask you how to calculate it. So you're not going to need to memorize this formula. You're not going to need to go through all this mess. In fact, what you're going to end up doing is you're going to pull it directly off the computer printout. So right here, we have the distance, and then we have, so basically you're going to look at your slope line. This here line of information represents the slope line. This is your X variable, this is your slope itself, and this is the standard error of your slope, or SB. So this is SB, or standard error of the slope, and that's where you find it, okay? I have 0.02037 just because I was a little more accurate, but 0.0204, they'll give it to you. It'll be on the computer printout. You will not need to calculate that, so don't worry about it. We need to show our degrees of freedom. Sample size -2 is 16. And chances are they're going to give you your T statistic, but if they don't, please remember it's B over SB, and that B is your slope. So basically it's going to be slope over standard error of the slope. And the slope you can either get from the calculator, because you can go stat test linear regression t-test, which is F, alpha trace. Make sure you have the not equal there, because that was what our null is. And we end up getting our slope is that little b, 0.0786. All right, so our slope is 0.0786. And you can also see that we have our standard, we also have our T statistic. If they ever ask you to, you could solve backwards to get to this value. Because if I took 0.0786 and divided by 3.86, I could solve backwards to get there, but I just don't see them ever asking you to do that, right? I just don't see that as ever going to happen. So stat test, and there's a couple things to keep in mind, and this very well could happen to you. So when we were able to run it with data, we actually ran the t-test. And when we ran the t-test here, we saw that we had a p-value of 0.03, 0.0031389. And it calculated it out very nicely for us. It's very likely, or it could happen. First off, it's usually on the computer printout. There it is. They rounded it. That's great. But likely on your test, these two values are likely going to be missing, and you're going to need to know how to calculate them. So you're going to need to know that if I take the slope, 0.0786, and divide it by 0.0204, I'm going to get 3.86. Now, once I have 3.86, I need to know how to get to the probability. Well, this is a t distribution, so here's how you do that. And you are going to need to know how to do this. If it doesn't come up on the calculator when you're working with data, you're going to go second bars, TCDF. There's our 3.86, taking it to infinity. Degrees of freedom happens to be 16. and we end up with this value. But there's a problem with that. And the problem is we ended up with this. We have a normal curve, or a t distribution, I should say, centered at 0 with the degrees of freedom equal to 16. But we have a t statistic of 3.86, but we took it to positive infinity. That's what we did. The problem is that's just a greater than. And what we really need is a not equal to statement. So in which case I need to come back and shade it this way, because remember, a p-value is the likelihood of getting a test statistic as extreme or more extreme. Well, just as extreme is 3.86. So that means that, if we're working with a not equal to, in other words, our direction doesn't matter, just as extreme as 3.86 is negative 3.86. So we need to be able to go this way. Well, I can calculate this, but since it's symmetric, I can just multiply by 2, and I get 0.001385, or rounding to their 0.0014. I would definitely make sure that I know to double this and how to calculate my p-value. With a p-value 0.0014, it's less than alpha, so we're going to reject the null. In other words, we're rejecting the fact that there's no linear relationship, so we rejected that so we can cross it out, and we now believe that there is a linear relationship between x and y. So our p-value is 0.0014. We reject the null. There is sufficient evidence that alpha equal 0.05 to suggest that the true population slope is not 0. In other words, we just restated the null. We just restated things. Then right here, we're restating the HA because it is not 0. So then I simplify it. This is my simplified. And please always include this. There is a linear relationship between airfare and distance traveled. In other words, there's some predictive value, okay? There is some predictive value. All right, moving on. That was hypothesis test. Confidence interval, I'm going to go through a little bit faster, only because we're using the same information that we just worked with. This is page 211 of the notes. So we have their distance traveled in miles. We've defined everything out, and we have to do that again. You have to do that. We've already done it, so I'm not going to do it again, other than say it's going to be the exact same as what we previously did. Our conditions are exactly what we worked with on the previous page. So I need to change these numbers real quickly. This is page 204, and this is 202 and 203. Walk through how to do that. So we've already got through the conditions. We've already done all of that. What we haven't done is actually write the equation down for the confidence interval for slope. Well, confidence interval for slope is just going to be basically B, our actual slope, plus or minus T star times SB. B being the slope, the sample slope, put a hat for sample, plus or minus T star, we'll have to calculate that, and then standard error of the slope, which we pulled from the table. So we have 0.0786. Once again, SB comes from right there, 0.0204. I wrote 0.02037, but really 0.0204. So where did I get T star? I'm going to get T star the way I always have, calculating T star. except my degrees of freedom is really important in this. So second vars, inverse t, the area, parenthesis, and we are doing a 96 confidence interval, 1 minus 0.96, close parenthesis, divide by 2. Degrees of freedom, 18 minus 2, or just the 16. And why do I get a different value? I'm not sure. I need to go back and check that real quickly. 1 minus 2, that appears to be correct, but I'm going to run it one more time. Test, excuse me, second vars, inverse t. Yep. All right, so this value right here appears to be incorrect. So I need to make an adjustment to that and make that negative, or make that a positive 2.235. And then I can go ahead, and if I actually want to run the endpoints, I either can multiply these out or I can just do it very rapidly. Stats, test, linear regression, this is G. And we have the confidence level, and we want to change this to 0.96. We'll store it there. And these values are also incorrect. How about that? I wonder if I rewrote that and didn't change the values. So I end up with 0.03307 to 0.12416 is my interval. Once again, we're not going to calculate standard error. They're going to give that to us. We are 90. I did change it. I changed it from 96 to 95, or vice versa. We are 96% confident the true population proportion, population slope for airfare relative to distance traveled lies within an interval. And our interval that we calculated is 0.03307 and 0.12416. In repeated sampling, we expect this method will capture the true population slope for airfare and distance traveled 96% of the time. Now, real quickly, what if this had contained 0? Well, if it had contained 0, we would say, oh, there's no linear relationship. But here, because it does not contain 0, I know it gets close. It does. But because it does not contain 0, there is a linear relationship between X and Y. All right, so there is a linear relationship between X and Y. That means it has some predictive value. We can measure that predictive value by 2 methods. The correlation coefficient, which was 0.69, which says moderately strong and the direction was positive. And I should say, we can use the coefficient of determination, which was 0.482. So 48.2% of the variation in airfare, or in Y, is explained by changes in the X, or in this case, distance traveled. But for our actual conclusion, we are 96% confident the true population slope for airfare relative distance traveled lies within the interval what we calculated, and in repeated sampling, we expect this method will capture the true population slope for airfare 96% of the time. So you see that it's very, very similar to our other hypothesis test. All right, thank you. And that closes out our notes on hypothesis tests and confidence intervals for slope. Thank you.